In the aftermath of the French Revolution, the old units of measure that were associated with the Ancien Régime were replaced by new units. The livre was replaced by the decimal franc, and a new unit of length was introduced which became known as the metre. Although there was initially considerable resistance to the adoption of the new metric system in France for a period of time, the metre gained following in continental Europe during the mid-19th century, particularly in scientific usage, and was officially adopted as an international measurement unit by the Metre Convention of 1875. History of definition. Universal measure. The standard measures of length in Europe diverged from one another after the fall of the Carolingian Empire. While measures could be standardized within a given jurisdiction, there were numerous variations of measure between regions. Indeed, as the measures were often used as the basis for taxation, the use of a particular measure was associated with the sovereignty of a given ruler and often dictated by law. Nevertheless, with the increasing scientific activity of the 17th century came calls for the institution of a universal measure, or metre cataleo, which would be based on a natural phenomenon rather than royal decree, and would also be decimal rather than the various systems of multipliers, often duodecimal, that coexisted at the time. Wilkins's idea was to choose the length of a seconds pendulum as the unit of length. Such pendulums had recently been demonstrated by Christian Huygens, and their length is quite close to one modern metre. However, it was soon discovered that the length of a seconds pendulum varies from place to place. French astronomer Jean Richer had measured the 0.3% difference in length between Caen and Paris. Little practical progress was made towards the establishment of the universal measure until the French Revolution of 1789. France was particularly affected by the proliferation of length measures, and the need for reform was widely accepted across all political viewpoints, even if it needed the push of revolution to bring it about. Charles Maurice de Talleyrand resurrected the idea of the seconds pendulum before the Constituent Assembly in 1790, suggesting that the new measure be defined at 45 degrees north. Despite the support of the Assembly, and of Great Britain and the newly independent United States, nothing came of Talleyrand's proposal. Meridional definition. The question of measurement reform was placed in the hands of the Academy of Sciences, who appointed a commission chaired by Jean-Charles de Borda. Borda was an avid supporter of decimalization. He had invented the repeating circle, a surveying instrument which allowed a much improved precision in the measurement of angles between landmarks, but insisted that it be calibrated in grades rather than degrees, with 100 minutes to a grade and 100 seconds to a minute. Borda considered that the seconds pendulum was a poor choice for a standard because the existing second was not part of the proposed decimal system of time measurement, a system of 10 hours to the day, 100 minutes to the hour and 100 seconds to the minute, introduced in 1793. Instead of the seconds pendulum method, the commission, whose members included Lagrange, Laplace, Monge and Condorcet, decided that the new measure should be equal to 1/10,000,000th of the distance from the North Pole to the equator, measured along the meridian passing through Paris. Apart from the obvious consideration of safe access for French surveyors, the Paris meridian was also a sound choice for practical scientific reasons. A portion of the quadrant from Dunkirk to Barcelona could be surveyed with start and end points at sea level, and that portion was roughly in the middle of the quadrant, where the effects of the Earth's oblateness were expected to be the largest. The task of surveying the meridian arc fell to Pierre Metre and Jean-Baptiste Delambre, and took more than 6 years. The technical difficulties were not the only problems the surveyors had to face in the convulsed period of the aftermath of the revolution. Metre and Delambre, and later Arago, were imprisoned several times during their surveys, and Metre died in 1804 of yellow fever, which he contracted while trying to improve his original results in northern Spain. In the meantime, the Commission calculated a provisional value from older surveys of 443.44 lines. This value was set by legislation on 7 April 1795. The project was split into two parts. The northern section of 742.7 kilometers from the Belfray, Dunkirk to Rodez Cathedral, which was surveyed by Delambre, and the southern section of 333.0 kilometers from Rodez to the Montjuïc fortress, Barcelona, which was surveyed by Metre. Delambre used a baseline of about 10 kilometers in length along a straight road between Melun and Lucente. In an operation taking 6 weeks, the baseline was accurately measured using 4 platinum rods, each of length 2 toises. Thereafter he used, where possible, the triangulation points used by Cassini in his 1744 survey of France. Metre's baseline, of a similar length, and also on a straight section of road between Vernet and Salses. Although Metre's sector was half the length of Delambre, it included the Pyrenees and hitherto unsurveyed parts of Spain. After the two surveyors met, each computed the other's baseline in order to cross-check their results, and they then recomputed the kilometer. Their result came out at 0.144 lines shorter than the provisional value, a difference of about 0.03%. Metre archives. While Metre and Delambre were completing their survey, the Commission had ordered a series of platinum bars to be made based on the provisional meter. When the final result was known, the bar whose length was closest to the meridional definition of the meter was selected and placed in the National Archives on the 22nd of June 1799 as a permanent record of the result. This standard meter bar became known as the Metre archives. The metric system, that is the system of units based on the meter, was officially adopted in France on 10 December 1799 and became the sole legal system of weights and measures from 1801. After the restoration of the Empire, in 1812, the old names for units of length were revived but the units redefined in terms of the meter. This system was known as measures usuels, and lasted until 1840, when the decimal metric system was again made the sole legal measure. In the meantime, the Netherlands had adopted the metric system from 1816, the first of several countries to follow the French lead. It soon became apparent that Metre and Delambre's result was slightly too short for the meridional definition of the meter. Arago and Biot extended the survey to the island of Formentera in the western Mediterranean Sea in 1806 to 1809, and found that 1/10,000,000th of the Earth's quadrant should be 443.31 lines. Later work increased the value to 443.39 lines. The modern value, for the WGS-84 reference spheroid, is 1.00019657 meters or 443.38308 lines. Nevertheless, the Metre archives remained the legal and practical standard for the meter in France, even once it was known that it did not exactly correspond to the meridional definition. When it was decided to create a new international standard meter, the length was taken to be that of the Metre archives, in the state in which it shall be found. The only significant international use of the meridional definition of the meter, apart from Metre and Delambre's original survey, was the initial work conducted by the British Association for the Advancement of Science on Electrical Units, which was to lead to the international system of electrical and magnetic units. It was often claimed that the international electrical units formed a coherent set of absolute units in the quadrant 11th gram-second system, where the unit length was the quadrant of the Earth's polar circumference. The unit mass was the 11th gram, or 10 - 11 grams, and the unit time was the second. Nevertheless, The precision of absolute electrical measurements in the late 19th century was not such that the 0.02% difference in the definitions of the meter had any practical significance. International prototype meter. With increasing international adoption of the meter, the shortcomings of the Metre-Des archives as a standard became ever more apparent. Countries that adopted the meter as a legal measure purchased standard meter bars intended to be equal in length to the Metre-Des archives. But there was no systematic way of ensuring that the countries were actually working to the same standard. The meridional definition, which had been intended to ensure international reproducibility, quickly proved so impractical that it was all but abandoned in favor of the artifact standards, but the Metre-Des archives were end standards. Such standards are prone to wear with use, and different standard bars could be expected to wear at different rates. The International Conference on Geodesy in 1867 called for the creation of a new international prototype meter and the arrangement of a system where national standards could be compared with it. The international prototype would also be a line standard, that is, the meter was defined as the distance between two lines marked on the bar, so avoiding the wear problems of end standards. The French government gave practical support to the creation of an International Meter Commission, which met in Paris in 1870 and again in 1872 with the participation of about 30 countries. The standard's international nature was ensured by a treaty, the Meter Convention, signed in Paris on 20 May 1875. The treaty established an international organization, the Bureau International des Poids et Mesures, to conserve the prototypes, which would be the joint property of the signatory nations, and to carry out regular comparisons with national standards. In recognition of France's role in designing the metric system, the BIPM is based in Chevreuse, just outside Paris. However, as an international organization, the BIPM is under the ultimate control of a diplomatic conference, the Conférence Générale des Poids et Mesures, rather than the French government. The construction of the international prototype meter and the copies which would be national standards was at the limits of the technology of the time. The bars were to be made of a special alloy, 90% platinum and 10% iridium, which is significantly harder than pure platinum, and have a special X-shaped cross-section to minimize the effects of torsional strain during length comparisons. The first castings proved unsatisfactory, and the job was given to the London firm of Johnson Matthey, who succeeded in producing 30 bars to the required specification. One of these, No. 6, was determined to be identical in length to the Metre-Des archives, and was consecrated as the international prototype meter at the first meeting of the CGPM in 1889. The other bars, duly calibrated against the international prototype, were distributed to the signatory nations of the Meter Convention for use as national standards. For example, the United States received No. 27 with a calibrated length of 0.9999984 meters plus or minus 0.2 micrometers. The first follow-up comparison of the national standards with the international prototype was carried out between 1921 and 1936, and indicated that the definition of the meter was preserved to with 0.2 micrometers. At this time, it was decided that a more formal definition of the meter was required, and this was agreed at the 7th CGPM in 1927. The unit of length is the meter, defined by the distance, at 0 degrees, between the axes of the two central lines marked on the bar of platinum iridium kept at the Bureau International des Poids et Mesures and declared prototype of the meter by the first Conférence Générale des Poids et Mesures. This bar being subject to standard atmospheric pressure and supported on two cylinders of at least 1 centimeter diameter, symmetrically placed in the same horizontal plane at a distance of 571 millimeters from each other. The support requirements represent the area points of the prototype, the points, separated by 4/7 of the total length of the bar, at which the bending or droop of the bar is minimized. Krypton standard. The first interferometric measurements carried out using the International Prototype Meter were those of Albert A. Michelson and Jean-René Benoit, and of Benoit, Fabry and Perot, both using the red line of cadmium. These results, which gave the wavelength of the cadmium line, led to the definition of the angstrom as a secondary unit of length for spectroscopic measurements. First by the International Union for Cooperation in Solar Research and later by the CIPM. Michelson's work in measuring the prototype meter to within 1/10 of a wavelength was one of the reasons for which he was awarded the Nobel Prize in Physics in 1907. By the 1950s, interferometry had become the method of choice for precise measurements of length. But there remained a practical problem imposed by the system of units used. The natural unit for expressing a length measured by interferometry was the angstrom. But this result then had to be converted into meters using an experimental conversion factor, the wavelength of light used, but measured in meters rather than in angstroms. This added an additional measurement uncertainty to any length result in meters, over and above the uncertainty of the actual interferometric measurement. The solution was to define the meter in the same manner as the angstrom had been defined in 1907, that is, in terms of the best interferometric wavelength available. Advances in both experimental technique and theory showed that the cadmium line was actually a cluster of closely separated lines, and that this was due to the presence of different isotopes in natural cadmium. To get the most precisely defined line, it was necessary to use a monoisotopic source, and this source should contain an isotope with even numbers of protons and neutrons. Several isotopes of cadmium, krypton and mercury, both fulfill the condition of zero nuclear spin and have bright lines in the visible region of the spectrum. Krypton is a gas at room temperature, allowing for easier isotopic enrichment and lower operating temperatures for the lamp, and so it was decided to select the orange line of krypton 86 as the new wavelength standard. Accordingly, the 11th CGPM in 1960 agreed a new definition of the meter. The meter is the length equal to 1,650,763.73 wavelengths in vacuum of the radiation corresponding to the transition between the levels 2p10 and 5d5 of the krypton 86 atom. The measurement of the wavelength of the krypton line was not made directly against the International Prototype Meter. Instead, the ratio of the wavelength of the krypton line to that of the cadmium line was determined in vacuum. This was then compared to the 1906 Fabry-Perot determination of the wavelength of the cadmium line in air. In this way, the new definition of the meter was traceable to both the old prototype meter and the old definition of the angstrom.